SwayamPrabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. So over the past few lectures we have been dwelling on this topic of root locus, and we've seen how, at least roughly, this tool of root locus can be used for analysis purpose, in the sense that if you're given a system, if you're given that you can vary this controller gain k, we've seen all possible locations of the closed loop pole. But now, today onwards, and maybe over the next one or two lectures, we shall actually look at root locus as a means of designing a compensator in order to make our closed loop system behave in a way that is desirable. Okay? We've already seen some glimpses or some hints of this in one of our previous discussions earlier. So please recall that when we considered this second order system, for instance, right, with two poles, we noticed that as it is left to itself, the root locus would be something like this, right? Yeah. So now we realize that if you want, for instance, to place your poles in such a way that you have a certain zeta specifications met. Now what is zeta essentially got to do with all of this? You see, in a very early lecture we've seen, when we talked about the performance of second order systems, we've seen that the zeta actually is the determinant insofar as the percentage overshoot is concerned. So we want a higher damping ratio, a higher value of zeta, and accordingly we might say that, okay, if we want to draw a constant zeta locus, then maybe it's something like this, okay, and this is probably our specification. So this will tell us that we probably want our closed loop pole, let me put it in a different color, we probably want our closed loop poles somewhere here. So then what is left to be done? Under these circumstances, all that we require to do is, we need to figure out what the value of that k is. Now we've already seen how to do that, right? So suppose you have this transfer function k upon, where k is this variable, it's basically the variable that you use to control the system, so to say, right? And you have s plus p1 times s plus p2, where let's say this is minus p2 and this is minus p1, all right? So now we know that obviously when we are trying to satisfy the closed loop characteristic equation, it turns out that s plus p1 times s plus p2 is equal to minus k. So obviously this angle criteria is going to be met. So all that we are then required to do is to evaluate the magnitude of k, which is then given by s plus p1 magnitude times s plus p2 magnitude. Now what is this s, you might wonder? Of course this s, remember, is a closed loop pole, and we already know from our requirements that this green location that we marked out on this diagram is our desirable closed loop pole location, right? So we just take one of these locations, we call this, let's say, S1. Of course S2 is going to be the complex conjugate of that, so I need not evaluate the gain separately. I mean, it's going to be the same gain after all, right? Okay, so for the value of k, if one of the poles has migrated to S1, the other will be just symmetric about this real axis at S2, right? So then what do we do here? What we are required to then do is to evaluate this, we just plug in this S1 plus P1 times S2 plus P2. But notice that essentially we don't do this sort of calculation, because after all root locus is a graphical tool, right? So what we instead do is we draw these lines, yeah, we draw these lines and measure off their lengths. So we call this L2, we call this length L1. So therefore our K turns out to be L1 times L2, and there we have our desired controller. So then the idea is that we set this gain of K equal to L1 times L2 in conjunction with this plant, which is 1 over S plus P1 times S plus P2, right? And then we sort of connect it in a closed loop negative feedback configuration, right? And we can expect that this step response, if we for instance apply this Rs is equal to 1 by S, then in the output the step response will have exactly the kind of percentage overshoot that we desire, which is given by the zeta level that we've chosen, right? So this is all very well and good. It seems like this choice of K actually gets us very far. However, it unfortunately isn't the case. So to sort of highlight that, now consider that you have a system with, say, this K upon S plus P1 times S plus P2 times S plus P3, right? So if I draw this open loop pole locations, let's say these are my 3 poles, minus P1, minus P2, minus P3, and I know that in such a case, of course, there will be some centroid maybe located somewhere here. I don't know, I'm not exactly computing this with some numerical values, but I definitely know the nature of the centroid. So what can I say about the root locus? It will be something like this. There will be a break in here, right? And then you will have an asymptote that goes along the 60 degrees, another asymptote that goes along minus 60 degrees, which is basically 300 degrees, and a third asymptote which will be coincident along the real line and go in this direction. So essentially the actual root locus would be something like this, yeah. So now immediately you see the complexity of designing the compensator increases even with the single K, and even then we might not have our desired closed loop poles. Why am I saying that? It will be clear in a while. So now suppose, again in the same by the same token as we've considered in the previous case, suppose someone specifies to us that we require this certain zeta, specified by of course the percentage overshoot that your system can tolerate or that is desirable, right? So you draw this constant zeta loci. What color have I used? Okay, blue. So let's say you draw this constant zeta loci. Well, let me use a different color here because I've already used blue for something else. So let's say this is your constant zeta loci, right? Now you see, because of this root locus, the only location where you can place your closed loop poles are these purple dots that I'm now drawing. Now in addition, someone might say that this is not good enough. I want this level of zeta, but at the same time I also want the pole more to the left. Why do I want that? Because remember, these vertical lines, these constant vertical lines were the constant settling time loci. So I might not be happy with this settling time, you see. So this overshoot might be acceptable to me, but the settling time that's provided by this particular root locus here may not be acceptable to me. What's worse is that maybe I choose this particular closed loop pole and then I evaluate K by measuring of this L1, L2 and L3, right? And then I notice that this third pole may be here. Remember, there are 3 branches of the root loci, so at that particular value of K which I have chosen, these 2 branches are migrated all the way up to here, which are fine. But let's say this third pole has migrated not too far. And what will tell us this? Well, one way is of course the last tool we discussed in the previous lecture, that's sensitivity. So for a fractional change, so for delta K upon K equal to something, say some x, the sensitivity will answer what is delta S upon S. So you just plug in this particular S here in this neighborhood, yeah, and remember this can be evaluated anywhere on the complex plane. It will in general be a complex number, but on the real axis you can clearly guess that it's going to be a real number, right? Because the closed loop pole is going along the real line here, right? So this is the question that is answered by the sensitivity question, and you might see that maybe for a significant amount of change in K, this really hasn't migrated significantly to the left. And why is that important? recall, now this system is a third order system, right? There are 3 poles and you're trying to approximate it by a second order system whose dominant poles you desire at some location like this. It may be that this at that particular value of k, this third pole hasn't gone significantly to the left. Why is that a problem? Because then we know that these are our dominant poles, and this is not following that 5 times the rule. So if this is sigma, then we want this 5 sigma rule to be valid in order to be able to ignore this effect of the third pole. But if this is not 5 sigma, so we ask the question, is it 5 sigma? Is it greater than 5 sigma? But suppose it is not, then clearly on multiple counts this design proves to be inadequate. So let me summarize that. First count is, of course, this is capable of meeting the percentage overshoot requirements because it clearly has some intersection with the constant zeta loci. But it may not simultaneously be able to meet the desired level of percentage overshoot as well as the desired settling time. This system may not be quick enough. Okay? So for instance, as I pointed out here, somewhere along this line, you clearly see that the intersection of this line with this constant zeta loci is somewhere here. But this point is not a valid point on the root locus. So clearly just by varying this k, I cannot place my poles arbitrarily or my closed loop poles arbitrarily at this location even if I want to. One limitation. Second limitation, if I want to approximate this higher order system by a second order system, then I must have this either the third pole is cancelled by a 0. Now of course there is no 0 here inherent. So that pole 0 cancellation question is out of the consideration. So the other possibility could be that, let's say, somehow this is following that 5 sigma rule, which is to say that if these dominant poles have a real part sigma, right, the magnitude is sigma, let's say, then this, the real part of the third pole is at least 5 times sigma or maybe more. But suppose that is not valid. I have found by this sensitivity analysis that by changing this k from 0 to this pole has only migrated so much to the left, which is still within this 5 sigma barrier. So in that case, this design is far from satisfactory, right? So this clearly motivates us to look for more sophisticated controllers. So this is after all a rudimentary controller, isn't it? Because this is just a static controller, just a k. There is no dynamics involved in this. But we can do better. We can actually design some dynamic controller. So how about trying to do that? The first idea that hits us is, look, immediately we see that if we want to actually place our pole in such a location that both the percentage overshoot and the settling time requirements are met, then I better put my poles here. But in order to do that, I'll have to make some changes in the controller structure. Just having control or just having a choice over this parameter k doesn't suffice. So one quick idea is, if you want to shift the root locus here, we've seen that for a second order system, we've seen this earlier, right, that the addition of a 0 on the left half plane has the effect of moving the overall root locus to the left. Now we wonder, is the same true of a third order system or higher order system? Let us try to find that answer. So suppose you have these 3 poles here, right, again as before, minus P1, minus P2, minus P3, right, and unadulterated or uncompensated, the root locus would look exactly like I've drawn in the earlier case. So I'm going to just repeat that again here. Of course, I don't need to draw the asymptotes now because you already know that it's going to be like this. Okay? But now, suppose I'm allowed to add a 0 on the left half plane. What effect will it have? Suppose I add the 0 here. Now you see the locations of the root locus on the real axis actually change. Alright? What else changes? The number of asymptotes will change. Here the number of asymptotes was 3. So remember, in the uncompensated case, number of asymptotes is equal to 3. But now once I've made this change, that is I've introduced this additional 0, now the number of asymptotes is equal to 2. Why? Because the relative degree of the plant has changed from 3 to 2. Now there's 1 0 added here, right? So apart from the fact that the locations of the root locus on this axis will change, so let me draw that, now instead there will be no root locus here, right. So the root locus will instead be here. And what else? This is also no longer going to be the root locus. Yeah, so this is sort of like crossing off with the purple line. Where else will the root locus be? Now you can evaluate the centroid. Of course, you have to take the sum of the real parts, and let's say this is z minus z. So now what you have is basically the centroid alpha is given by minus p1 minus p2 minus p3 plus z upon, now the number of poles minus zeros is 2. So you see immediately you will have a change in the location of, and most likely the centroid will shift to the left. Why? Notice the numerator has decreased, but the denominator has decreased much more, right? In general, we can assume that. Okay? I mean, these are not really, unless you take actual numerical values, it's hard to analyze. But let's say you have this P1, P2, P3 here, and the Z is actually in between a pair of these, right? So of course, you can assume that the worst case would be if this had cut off this, right? So then maybe the centroid would have been somewhere here. Anyway, we are not really bothered about that. The fact that the centroid has changed, it might move to the left, it might move to the right, most likely it will move to the left, depending on some realistic values. But of course, you might choose your 0 to be far to the left, in which case your centroid will actually shift to the right. Yeah, your original centroid was here, but now your actual centroid with the compensated system, with the addition of a 0, will shift. Now how it will shift will depend on which term is affected more. If the denominator is like if the denominator reduction in the denominator, yeah, is much more than the reduction in the numerator, then of course this alpha will increase in magnitude and you will have this move to the left, right? So of course it will depend. So let's not jump to any conclusions, and we'll see that this really becomes an interesting question, things like these. Anyway, so but the more importantly, what happens is now the directions of the asymptotes are along 90 degrees and along 270 degrees. So now you see, provided that this alpha, so we know that this alpha now belongs to the left half plane, right? Because we haven't shifted this 0 much to the left. If you shift the 0 far to the left, then this positivity far outweighs all these three negatives, no? So then it might happen that your centroid actually shifts to the right. But since this centroid is actually, since the 0 is actually between P2 and P3, minus P2 and minus P3, so at least it has not been able to cancel out the effect of minus P3. So this quantity on the numerator, even if it is less than earlier, it is still negative. So therefore the centroid is still on the left half plane. So we don't have to suppose that really. For this configuration, we know that the centroid is in the LHP. So somewhere here, let's say the centroid starts, let's say somewhere here, right? But now the asymptotes are like this. So again, like we concluded for the second order system, you see the root locus now will go in this direction, right? So this is now the compensated root locus, and immediately you see, if you draw the constant zeta line, without the 0, you are forced to place your closed loop poles at that particular value of zeta here. But now, with the 0, you can now place your pole here. Notice that even if this centroid was somewhere here, because the angle has now changed, this was actually a 60 degree angle that this asymptote was making earlier, now this asymptote is making a 90 degree angle. So there is a net shift at least on the left, to the left, right? But this also brings something interesting, as this brief discussion that I made on the location of the centroid might suggest to you. Notice that in an earlier lecture, when we talked about the second order system like this, we said almost uncritically that if you place a 0 on the left half plane, yeah, and if you keep moving the 0 to the left, it has the effect of pushing your root locus further and further to the left. Yeah. So we saw that for a second order system, it was invariably true that the more you push your 0 further to the left, yeah, the more you push your 0 further to the left, the root locus moves to the left. But now for a third order system, it is actually quite the contrary, right? Why is it so? One reason is, of course, the second order system had only one asymptote which was along this direction. So no matter what you did to this original unadulterated or uncompensated system here, yeah, even that uncompensated system never had any tendency to go to the right half plane. But now this system had a tendency to go to the right half plane, and there are more parameters to play around with. So now I am asking a different question. The first question was, what about the uncompensated system with no zeros? And then we saw that if we introduce compensation, if we introduce a zero, right, it has the effect of shifting the root locus. Compared to the uncompensated system, it has the effect of shifting the root locus to the left, at least because of the angle of the asymptote, even if not for the location of the centroid. But now, suppose the question is, you are allowed to play around with the location of this z, with the location of this zero. Suppose it's like a sliding game, it's like a rheostat. So you are, suppose there's this slide along which, there's some graphic user interface which allows you to slide this zero, and you are interested in asking the question as to what will be the effect of the root locus of the compensated system. So now we are forgetting about this uncompensated system with 3 asymptotes. Now from here on, our question is where to place this zero. We've understood that placing a zero helps us in improving the system's performance compared to the uncompensated system, because quite simply the angle of the asymptote itself has changed. But the key question now for a designer is, because now we are interested in designing this compensator, right? So now apart from this k here, we are also introducing this compensator, right? So the critical question for us is where to place this zero, yeah? And let's take a closer look at this then. Once again, so now we will always consider that there is some zero, alright. So one way of answering this question is, of course, to analyze how the centroid shifts. Think of the centroid. The centroid is given by alpha is equal to minus p1 minus p2 minus p3 plus z, right. So this is minus p3 minus p2 minus p1, yeah. And suppose you place your zero here, yeah, larger than all 3 of them. What happens then? You see, if you keep shifting this further and further to the left, this becomes more and more positive, but this remains constant. So at some point, of course this is going to be 2, so at some value of z, yeah, this is minus z, so at some value of z, alpha is greater than 0. In other words, the location of your centroid would probably be somewhere here. Let's say this is alpha. In other words, that means that the asymptotes would then be like this. So you might expect that then your root locus would look something like this. Which is clearly something that we don't desire. So already we see one difference. You see, in the second order case, we almost invariably concluded conclusively that the more you shift your 0 to the left, the more the root locus shifts to the left. But as soon as you introduce a third order system and study the effect of an additional 0, you see that pushing it more and more to the left doesn't have the same effect. So you should not be very wary of these blanket statements. Always apply the rules of root locus that we've learned. Those are of course not rules, basically a bit of application of the angle criteria, as we've seen. Now there's another way of seeing this, of course it helps even if you've forgotten about this centroid formula. Suppose that with this, so there are 2 potential locations of this z, say, for instance, yeah. So this is, let's say, z, and then you've shifted it to here, let's say this is z dashed, minus z dashed. So with z, suppose this is a point on the root locus. So this point satisfies the angle criteria. In other words, it means that if this is theta 1, this is theta 2, this is theta 3, this is theta 4, then you have theta 4 minus theta 1 plus theta 2 plus theta 3 all taken together is equal to some odd multiple of pi, right. But now suppose you've shifted this here. See, you're not changing this open loop poles, you're only shifting the 0. Now what do you think at the same point, let's say S1, what do you think is going to be the contribution? This theta 4 is going to reduce, no? So as Z moves to, as minus z moves to minus z dashed, theta 4 reduces, isn't it? This is an even more acute angle now. So if theta 4 reduces, this point no longer satisfies the angle criteria because this remains constant. So theta 4 reduces. Now in order for this to be balanced, the only thing that can change is this S1. So where does S1 shift? Notice that if S1 shifts to the left, of course then theta 4 again increases, but so do these three fellows, right? And there are 3 in number. So it is probably reasonable to expect that if you move this point S1, suppose, okay, let me write it formally. Suppose S1 is a point on the root locus for 0 at minus z. We are interested in asking this question, how does S1, how does S1 shift as z moves to z dashed, which is more to the left, yeah? And one way we have of course seen of answering this question is to study this centroid, and that clearly tells us that, you know, eventually it's going to move to the right, the root locus is going to move more to the right. But the other way to see this is now apply the angle criteria at the old point S1, yeah? So of course this S1 is definitely a point on the old root locus with the 0 at minus z, so of course it satisfies the angle criteria. But now as soon as you move this 0 to minus z dashed further to the left, now see this angle theta 4 has reduced. So if theta 4 has reduced, then we must require that these 3 must also reduce, but keeping S1 unchanged, these cannot reduce. So S1 must move because these points are fixed, the poles we have no control over, yeah? So then which way should S1 shift? Should S1 shift to the right or should S1 shift to the left? Let's say S1 shifts to the left, yeah? So if S1 shifts left, then of course theta 4 increases, yeah? If you shift S1 here, from here, if you say this is S1, so of course then theta 4 will increase, theta 4 will increase. So maybe this is a candidate point, but remember, so do theta 1, theta 2 and theta 3, and they are in fact threefold in number, right? Yeah. So of course this is just a qualitative argument. I am not saying that this is going to be true for every single point, okay? But I am just taking some arbitrary point, let's say close to the crossing over here, or let's say somewhere here, yeah, not very close to the real axis. These are all very qualitative arguments. You need to actually put in actual numerical values. In fact, the reason why I am not very satisfied with this centroid based argument is because this will only tell you about the asymptote, but what happens around this region may still be shrouded in mystery, right? But notice, if you shift S1, if you consider a point to the left of S1, say S1 dashed, then it is true that theta 4 decreases and potentially maybe we can still meet this angle criteria, but so do these fellows, right? On the other hand, if S1, if S1 moves right, in other words, if the candidate point on the root locus now shifts to the right, so for example some point here, let's say S1 double prime, okay, at S1 double prime, then notice that at S1 double prime, it is true that z dashed, the angle subtended from this arc z1 dash, z dash to S1 prime has decreased. So that means theta 4 decreases further, but so do theta 1, theta 2 and theta 3, and these are 3 in number once again, right? So an incremental change, if you take, if this change in theta 4 is delta, then probably the change in theta 1, theta 2 and theta 3 is 3 delta. I mean, just roughly speaking. I am not just saying this as an accurate one, you probably need to do a sensitivity analysis with respect to z, right? You probably need to do a sensitivity analysis of the closed loop pole with respect to Z in order to come up with exactly how it changes. Remember, you need not only carry out the sensitivity with respect to K. Sensitivity of anything can be carried out with respect to any other variable. So in order to get an accurate answer, you must resort to the sensitivity question, but I am just trying to give you a rough sketch. So therefore, it seems more plausible that this S1 double prime is going to be the new point on the root locus. If you move the pole, if you move the 0 to the left, the actual root locus probably moves to the right, not just asymptotically, but even at some arbitrary point like so. Of course, you shouldn't take it as a blanket statement. I am just showing you that there is a possibility that this happens, and a very good possibility that this happens with the 3-pole scenario, unlike the case where we had only 2 poles. So things change as you increase the order of the system, as you increase the number of poles, yeah, system complexity increases. So you should not have any such preempted impressions in your mind, some premeditated ideas that this is what always happens. I add a 0, this happens. I add a pole, this happens. No. Those conclusions you can make subject to some assumptions that there are only 2 poles, so you add a 0 to the left, it has the effect of shifting the root locus to the left. You add a pole, an additional pole, it has the effect of shifting the root locus to the right. Yeah, those are very special cases, but do not go under this hypothesis that it's always a very good idea to have a 0 as far to the left as I like, irrespective of the degree of the actual system. Okay, so that's a point. So now, based on all of this discussion and this previous slide that we had, it seems like, it's a good idea to add a 0 nonetheless. Maybe not to the extreme left, but at least it's better than the uncompensated system, right? Because the uncompensated system didn't allow me much flexibility. But now, let's say I want to test how good this additional 0 is. Yeah. So let's take that again, that 3-pole system. So minus P1 minus P2 minus P3, right? And I have this desired percentage overshoot given by this constant zeta line here. So again, to draw this at the cost of boring you, I'll again draw this root locus like this and this branch here, right? So clearly, let's say we are not happy with these 2 closed loop poles. Let's say we desire a settling time criteria as well. We want to meet a settling time criteria as well. So what settling time criteria should we then meet? Okay, suppose we want a settling time like this. Yeah. So once we have specified, note that once we have specified the settling time and the percentage overshoot, we have a unique location on the complex plane. So this is our desired closed loop pole. Now the question is, how can we design a closed loop pole here? Of course, we have seen that clearly using just K. So let me make that using, so let's say this is PC1, PC2. So minus PC1 minus PC2. Of course, these are complex numbers. It doesn't matter if I put the minus sign nonetheless. So using K alone, it is impossible to place closed loop poles at minus PC1 minus PC2. Then what are we to do? Of course, let us use the weapon that we've just learned. What is that weapon? An additional 0. How do we go about this? Again, it is the angle criteria. That old friend of ours, angle criteria. Remember, that's the reason why we say that everything about root locus is just hinging on this angle criteria. What do I mean by that? Suppose you want this to be a point on the root locus. Yeah. Then, so this is our observation, if PC1, PC2 are to be points on root locus, they must satisfy the angle criteria. We call this AC in short. So they must meet the angle criteria. So if they want to meet the angle criteria, what do I need them to do? I need that at this point, the angle subtended by this the angle subtended by this and the angle subtended by this, yeah, clearly they will be inadequate because the uncompensated system does not satisfy the root locus angle criteria here. So let me say this is theta 3, theta 2, theta 1, but I have one last throw of the dice, right, one last roll of the die. What is that? I can actually place a 0, and how is that going to help? So now compute theta 1 plus theta 2 plus theta 3 with a minus sign, right, yeah, and solve for some theta z minus, these are constant, this can be computed, no, this is a constant. Given that I have fixed this point minus PC1 or minus PC2 for that matter, I know that these lines are uniquely defined because P1, P2, P3 are fixed. So all these 4 points are fixed, so I can clearly measure these lines. Yeah, remember root locus is a graphical technique. So just like we did here, we measured this lengths, here also we will just measure this angle with a protractor. Yeah, not a big deal. But now I am going to solve for this. So what value of this theta z will actually satisfy this angle criteria? Yeah, this is a constant, let me call this x, is equal to some 2l plus 1 pi, alright. And now you notice that this tells me that theta z should be this 2l plus 1 times some odd multiple of pi plus this x, or rather if I have denoted it by a minus sign, then it should be minus x. Yeah. So this whole thing is minus, this whole thing is x, yeah. If this whole thing is x, then of course it's minus x, yeah. Now what am I going to do? I am going to search for a point here on this real axis because I am going to place one single real 0. I am not going to put a complex conjugate real zeros, okay. So I am going to put just one single real 0, and if I want to do that, then what I need to compute is basically what point on this real axis. So then question is, which point on real axis satisfies the condition that theta z is equal to the angle joining the angle that the line joining it, so it's the point, that's the it, which point on the real axis satisfies the condition that theta z, the angle is equal to the angle joining the line joining it to PC1 equals 2l plus 1 times pi minus x. Yeah. Once I have answered this question, I will just put the 0 over there and done, voila. So let us say I place the 0 over here and I find that this particular theta z1 or theta z, so let us say this is the theta z, so I place my 0 here, that this is my minus z, and I am done with the controller design. So this is called basically a controller of the form k s plus z. Why do I need the k still? Remember, at this point I have to now still determine what the value of k is. So what is going to be the value of k? What is k equal to? That is the next question. So in order to evaluate that, we have to just compute the lengths of certain lines. So let us say again I draw this line, this is L3, this is line joining this is L1, line joining this is L2, and this new 0 that I have now added, let me just call this L, yeah. So now I just measure it off and I just say that k is going to be nothing but L1, L2, L3 upon L, right. It is the same thing that we did here, no. All the lengths from the poles, length of the segment from the placed pole appear on the numerator, and from the 0, of course there was no 0 here, so nothing appeared in the denominator. Here there is a 0, so this L appears here. Yeah, this L is this, maybe this blue one. Yeah, all right. So this completes the design of this controller. So this is called a PD controller. Okay, this is called a PD controller, in short PD, but the actual name is proportional plus derivative controller. Why proportional? Of course, because of the term k here. Why derivative? Yeah, so you see k times z is going to be the proportional part. Why the derivative? Because remember this s times anything in the Laplace domain is akin to taking a derivative of the time domain function, whose Laplace transform it is that you are multiplying with the s. So therefore it's a proportional plus derivative controller. So apparently all is well. In addition, as an offshoot of this, we have also done something more. We have actually, even though we didn't originally target that, we have actually improved the steady state error performance. Why do I say that? Notice, of course again this is subjective and you will have to take some numerical examples, which we will do maybe in one or two, in the next couple of lectures or so, we will take an example. But notice that what is this steady state error dependent on? The steady state error, so steady state error depends on k G0. Now what is G0 after the compensation? So G0 after compensation is amplified by Z. Why do I say that? Because now the overall compensator is, you had k times s plus z upon s plus p1, s plus p2, s plus p3, right. So earlier this was your GS, and the uncompensated GS was equal to some other k. Yeah, this is very critical. So this is some k2. So it's not exactly an amplification of Z. So you see this is s plus p1, s plus p2, s plus p3, right. So this is going to be, so this implies that G uncompensated 0 was some k1 upon p1, p2, p3. But after the compensation, so this is G compensated, so the G compensated is now k2 times z upon p1, p2, p3. So this makes sense, it is amplified by a factor of z, and typically z is greater than unity, in fact much greater than unity in most cases. So for example here it could be much greater than unity. So this z actually has the effect of increasing G0. And why is this G0 important? Remember that E steady state was given by 1 by 1 plus G0, whether it is the compensated one or the uncompensated one, right. So as you increase this G0, this steady state error decreases. But there is a catch here. This amplification does not come alone. Remember, we have to also be able to compare this k1 and k2, and we already know clearly from this that the k that was originally there, of course the k was originally not here, the k was originally here, but now the k that was originally here, apart from just multiplying by these distances of from the 3 open loop poles, now it gets divided by the distance from the 0 that we have introduced. Yeah. So it is not very straightforward to really say whether k2 is greater than k1 or k2 is less than k1, apparently at this juncture. But we will later see, we will see with examples here that if you actually desire to push your poles onto the left, the closed loop pole to the left, yeah, and typically if you follow this line, then it gets basically further and further from the real axis. Notice that this was the uncompensated system's closed loop pole, this is the compensated system's closed loop pole, right. So these L1, L2, L3, they also increase significantly in the compensated system, right. So even though this L1, L2, L3 now gets divided by this L, unlike in the uncompensated system where it was just the product of L1, L2, L3, but these lengths have significantly increased. So In general, of course, at this point it might seem like I am doing a lot of hand waving, but when we actually deal with real numbers, you will see that it's true, that this L1, L2, L3, this product has increased manifold times. So even if it gets divided by this L, yeah, this L probably this length of the line from the newly introduced 0 to PC1, that is L, it might actually be almost equal to one of these L1, L2, L3. There are still the other two factors remaining, but these other two factors have increased so much that now the product of any two of these factors is greater than the erstwhile product of all three factors in the uncompensated system. You follow? So earlier you had K1 is equal to L1 hat, L2 hat, L3 hat, but now you have K2 is equal to L1, L2, L3 upon L. Now it is true that it gets divided by L, but even if this L is suppose comparable with one of these fellows here, right, you still have this L1 and L2, and remember this L1, L2, L3 is much greater than L1 hat, L2 hat, L3 hat, and the reason being that in general if you are following along this line, you are only going further and further from the real axis, and therefore you are going further from any point on the real axis. Okay, so in general it appears like there is only a scaling factor of z, but in reality this K2 also increases compared to K1 in the uncompensated system, right? Okay, so therefore it has the effect of actually increasing this G0 manifold times, and that increase reflects in a lower steady state error. But you might still not be very happy with this. You might say, I want even lower steady state error, I want a zero steady state error, and why not? After all, I know how to do this. I know that if I employ a proportional integral control, an integral action, if I make this plant somehow type 1 in open loop, then it will give me zero steady state error to a step response, a step input. So why not? Yeah? Why settle for something less? Right? So therefore, we don't stop just at designing this PD controller, we also design a PI controller thereafter. So how do I design this PI controller? Now, notice the compensated systems root locus. So we are going to start from this compensated systems root locus. Suppose the compensated systems root locus, there are zeros, there's this additional 0 that I have now introduced, so this is minus P1, minus P2. So this is a two-stage design. First stage we have designed the PD controller, the proportional derivative, and the second stage now we will design the PI controller. What is the philosophy behind this design at this stage? You see, we are already there, we are already at the desired closed loop pole, so we don't want to tamper with the location of the closed loop poles by much. Yeah, we don't want to mess around with the location of the closed loop pole. All that we would be happy to do is, let's just say that we can place very surreptitiously, if we can place this one pole here at the origin without disrupting the angle criteria, yeah, then we are happy. How do we do this surreptitiously? The moment we add this pole here, yeah, you notice that now if you add a pole here, a point which was earlier on the root locus now will no longer satisfy the angle criteria, because after all this entire angle gets added. This entire new angle, this theta P4 now gets added. So how can you ensure that after addition of this theta P4, you will still meet the angle criteria at this point? You cannot. There is a solution. Solution is, if I at the same time place a 0 also very close to this. So if I place the 0 very close to this, then maybe it is not exactly at that same old location where I had placed this closed loop pole at PC1, but at least in some neighborhood of this, yeah, I have hope, maybe a little to the left or a little to the right, somewhere within an epsilon ball of this, yeah, depending on how close I have placed this pole and 0 pair. Remember, this pole and 0 pair has but one job to do, yeah, nothing to do with pole placement. The pole is already placed where it was, where we desire it. This is only being introduced to improve the steady state error. We want zero steady state error. We are not just happy with reduced steady state error like the PD compensator gives us. So we want to have zero steady state error. We are more greedy. We demand more out of our system. So that is what motivated us to introduce this pole at the origin. But the moment we introduce the pole at the origin, we introduce a new problem. The new problem being that no longer is this point going to satisfy this angle criteria, and therefore the closed loop pole will now migrate far off possibly. So how do we account for that? Place a 0 very close to this, okay. Now once you put this very close here, right, once you place this pole very close, pole and 0 pair very close by, like so, then you see that the net contribution by this theta P4 and this, let's say this theta Z2, yeah, these are almost comparable. So if not exactly at the theta P, if not exactly at PC1, sorry, so this was the original PC1, at least within an epsilon ball of this PC1, around this PC1, somewhere here maybe, PC1 prime, or maybe somewhere here, which we really don't mind, that much leeway we can make. So at least somewhere close by, we will have the closed loop pole, yeah. But in addition, the benefit we are now getting in exchange for this small trade-off in the exact location of the closed loop pole is that now we are getting 0 steady state error to a step response, and that's a big deal, right. So therefore, we go for this, okay. So at the first stage, remember, we place the closed loop poles to ensure desirable transient behavior. In the second stage now, we design this, this 0. And notice, because we have placed these two very close by, around this point, if you now want to evaluate the k length also, because remember this k will now be this L1, L2, L3 by L that we had earlier taken, and now it gets modified. So let me change the color of this. So earlier we had, let's say, L1, L2, L3 upon L. Now you have this LP4 upon LZ2. But remember that this is comparable. This is comparable. And because this is comparable, so this k bar now, so this is almost equal to k, which is this. So this is k. So this is almost equal to k because this is almost equal to unity. Why is this almost equal to unity? Because from a point which is the closed loop pole, which is reasonably far from the origin, just placing a pole and 0 pair very close to the origin, yeah, the distances are almost equal, viewing from a vantage point of this PC1. Yeah, so therefore we are good. But one caveat, you should never ever rest easy with such a design and feel that you have done your task until you carry out a simulation. Because remember, all of the derivation and everything that we did for the settling time and rise time and all these performance metrics, the percentage overshoot, were under the assumption that we are dealing with a second order system. But clearly here we know it is not a second order system. So where could the problems arise? For instance, you might feel that you have placed this pole and 0 close enough, but let's say at that particular value of k bar, this pole isn't cancelled. I mean, you see, let me just enlarge that. So there's a pole here, there's a 0 here, then you have the original poles of the PD compensated system. Yeah, so this is the PD compensated system, poles and zeros of the PD compensated system. So clearly now, you will have a branch of the root locus here, you will have a branch of the root locus here, and you will have a branch of the root locus here. Yeah. So now if this has to be, let's say something like this, suppose, yeah, it's still a relative degree 2 plant, yeah. I don't know, I'm just drawing it like this, I'm just assuming that this is the asymptote, yeah, just like that. So now, remember that if this is where your desired, this PC1 is, and minus PC2 is, right. So now remember that at this location, you have these two fellows migrating here. But what about the other poles and zeros that you have introduced because of the compensators? Yeah, there's also this third pole. If this has to behave like a second order system, what should ideally happen is that there should be a cancellation between these two. Yeah, there should be a cancellation between this pole 0 pair. There should also be a cancellation between this pole 0 pair. But what if this value of k bar that you attain at this point, at that value of k bar, this branch is not sensitive enough. In other words, this closed loop pole starting from k is equal to 0 here has not migrated sufficiently close to this 0. Yeah, then you still have this pole 0 pair to contend with. This makes your system deviate from the ideal second order system assumption that you've made, and therefore Even if you think that okay, the dominant poles are here, in reality your dominant poles are not there. What's even worse is this PI compensator that you have introduced now, this PI controller that you have introduced. Now this branch must need necessarily be very close to the 0 that you have introduced. Suppose, remember that as k is equal to 0 it's here, as k is equal to infinity it's here. So all the entire journey from k is equal to 0 to infinity is encapsulated in that small branch, in this small branch here. So you can reasonably expect that this branch is not going to be very sensitive to changes in k. So maybe this value of k is not large enough. Yeah, if this value of k is not large enough, then probably this pole in closed loop hasn't migrated close enough to this open loop 0. And if that hasn't happened, right, if that hasn't happened, then in the process of introducing this pole 0 pair here and the 0 here to improve the performance, you've actually made it much worse, because you've actually introduced a slower mode. So this no longer is the dominant pole pair. So what is the way out for this? Do you keep computing like this? No. That is why we have simulation tools. And remember, this is the caveat. Anytime you're designing a controller using root locus, later on we shall see when we do state space methods, we shall see more sophisticated methods of controller design. But as far as root locus is concerned, whenever you're designing compensators or controllers using root locus method, you should always simulate. If your simulation isn't good enough, if it doesn't meet the percentage overshoot requirement, yeah, or the settling time requirement, it means that this idealization that you made about the second order assumption of this dominant pole pair is not valid. Maybe you need to rethink where to place this pole 0 pair. The pole is of course fixed at the origin because it's a PI controller, right? So basically you have now designed this k by s, yeah, ki by s, maybe you've just introduced a 0 here, right? So this basically is something like a s plus z upon s, right? S plus z1 or z2 rather upon s. So you've introduced a pole at the origin and a 0 at z2. Now remember, the moment you've done this, you have to be very careful that this, in the closed loop at least, this branch comes reasonably close to this z2. If not, then this slow mode will have a large enough residue when you expand by partial fractions. Yeah, there will be a large enough residue for this slow mode, which is probably migrated from 0 to maybe some small minus epsilon, but it's still far off from this this z2, this minus z2, right? So there are these potential problems. Of course, we don't go into calculations because this is meant to be a graphical technique. So what we do is, once we've designed this, we simulate. If the simulations are satisfactory, we just complete the design and say that we are done. If it is not satisfactory, we have to rethink not just this PI controller design, we might even have to rethink the PD controller design, right? We might have to say, okay, maybe we cannot actually sort of place this here, right? Maybe we have to rethink. So if this is our minimum zeta, maybe we try to relax this a bit. Maybe we want to allow a larger percentage overshoot. Maybe we want to allow a larger settling time value, that is a slower system. Who knows, right? So that is why we have to be very careful about this. None of this design, no design using root locus is ever complete without a validation using proper simulations, okay? In the next lecture, we shall start with what is called lag compensator, lead compensator and a lag lead compensator, and we shall see why we are in the first place motivated to use them. Apparently, yeah, the same problems that we have of verifying using simulations are still there within those lag and lead compensators, and yet we want to go for those compensators instead of this PI or PED or PID controller, yeah. So when you put this whole block together in conjunction, you have one S plus Z times S plus Z2. So this is going to give you the structure of a so-called PID controller, okay. So this is how you design a PID controller using root locus technique. Yeah, so in the next lecture we shall see that there are some problems with implementation of this PID controller in the sense that they require active circuit elements, yeah, which is what motivates us to go for the approximate versions of these PID controllers, because these PID controllers are extreme cases of a lag lead compensator, yeah. So next lecture we shall see an approximation of this PID using a lag lead compensation, which can indeed then be realized using our standard circuit elements comprising only passive elements such as inductors, resistors or capacitors, maybe only resistances and capacitors alone, right. So till then, take care. Thank you.